continuing with the review for the semester exam. Number 44 goes back to electrostatic charges. It says, which diagram best represents the electric field surrounding a positive charge? So it goes out of positive and into negative. So this shows it going out, which the answer is A. Okay, so now we have a concave mirror, and they tell us that the focal length F is equal to 0.10, and it says if an object is placed at point B, which is here, so that's between the focal point and the mirror, it says what is the image. Now for the different types, I think we had some type of a chart where instead of calculating it, again, if you want, you could do the ray diagram. Does everyone remember how to do the ray diagram? We go parallel and then through F, and then we go through F and parallel. So there's more than one way to do this. So you could either do the ray diagram. Sometimes people remember the different scenarios. We only have this, so as far as calculating it, you're not going to, this isn't the type of thing where you're going to bother calculating anything. Okay, so you either do the ray diagram, or if you don't do the ray diagram, then you remember from like the table that for concave mirrors, if the distance from the object is greater than the center of curvature, the image is real. If it's in between the focal point and the center of curvature, it's real. But if it's in between the focal point and the mirror here, it's always going to be virtual. And then this way it's always. So you could either look at the table or you could just draw the ray diagram. Okay? So this one is going to be virtual and erect. If the object is placed at point D, its image will be located between, and that's going to be between F and C. So again, probably the easiest way to do this is to do the ray diagram. Or again, you could look at knowing that when we had the different types of mirrors, that for concave, if you have F, and F is always going to be positive, because whenever we do this, this is going to be a frame of reference, and then depending upon what DO is, so if DO is greater than the radius of curvature, or we call it C, if C is between DO and F, and then F is greater than DO, which is greater than 0, that this image is always going to be real, real, and virtual. And this one is going to be reduced and inverted. This one's going to be enlarged and inverted. And then this one's going to be enlarged. I think the best way is to do a ray diagram. That's why it's important to keep your notebook. This is very small here, but you have all the worksheets that we did when we did that, where we did lots and lots of practice doing ray diagrams. All right, number 47, that one you're going to have to do a calculation. So for the calculation, you need to know that the radius of curvature is equal to twice the focal length. The way that I remember it is I always remember that F is equal to C over 2 or R over 2, because C is the radius of curvature. So that is equal to 2F, which is equal to 2 times 0.1, which is 0.2. So you weren't using the main equation. You know, the main equations for mirrors and lenses, 1 over F is 1 over DI plus 1 over DO, and then HI over HO is negative DI over DO. So we're not using those here. Okay? We will use it on the next one. The next one says, an object 2 meters tall So as I'm reading it, this is the height of the object. So I want to identify that. Again, when you're doing the test, you should hold your scrap right next to the test like this. So maybe you could write here HO is equal to 0.2. It's placed 0.5 meters to the left of the mirror, so that's going to be DO. And then it says the image is located 0.3 meters to the left, so that's going to be DI. And now it says to find the size of the image. So we want to find HI. So again, we're going to use our equation hi-ho is equal to negative di-do. I would go ahead and cross-multiply, because otherwise I'd make an algebra mistake. And we know that on standardized testing like this, whatever the most common mistake is one of the multiple choice answers. So HI is equal to negative DI. And then I would just substitute in my values, and then I get the answer as 0.4. Again, here we have to practice doing lens diagrams, but as far as this is concerned, they give us enough information that I would just always use the equation first. So it says that an object which is 0.2 meters high, so that's the height of the object, is equal to 0.2. The object is located 0.5 meters, so that's going to be the distance of the object. And then it tells me the focal length is 1. So I see already that I have enough information that I can use either one of the two equations that we have. So it says how far from the lens is the image. So how far from the lens is the image, we want to find DI. So we're going to use the equation 1 over F is equal to 1 over DI plus 1 over DO. Even though we know how to do it algebraically, if you notice on the scrap paper that has all the equations you're going to be using on the semester exam, we already rearranged that one for you. So DI is equal to DOF over DO minus F. So when I substitute in my values, that comes out to be 1. And again, you need to practice doing these yourself. All right, the image would be described as, so the object is going to be between F prime and the lens, so that one's going to be virtual and erect. Remember, when you look at the signs, if something is, depending on which side of the lens, it's going to tell you whether it's virtual or real. Whether it's right side up or upside down, it's going to tell you whether it's erect or inverted. The smallest image of the object would be located when the object is at 4F. And again, this has to do with understanding the characteristics of, you don't want to sit here and put numbers in because you don't have time to do that during the test. So for convex lenses, again, if we look at a positive focal point and we look at things like DO, where is that object located in reference to the lens? So if it's located greater than 2F, between 2F and F, and then if it's between F and the lens, how's the image? So we know that, in this case it's real, in this case it's real, and in this case it's virtual. And then here it's reduced and inverted. In this case it's enlarged and inverted. And then in this case it's enlarged. It says if the object were moved towards the lens, so when you're moving it towards the lens, what's happening is you're decreasing the distance, the DO. If the object was moved towards the lens from the position showed, the distance from the lens to the image, so it's obviously going to decrease. I don't even think that has anything to do with physics. I mean, obviously, if you're moving it closer to the lens, DO is going to decrease. So that's more of like a definition of what's the distance of the object. And then the last question says, if the object were moved towards the lens from the position, the size of the image would decrease. So if you look at the equation, HI over HO is equal to DI over DO, we see that, again, that the image itself is going to decrease as you do that. All right, number 54. Which diagram most accurately represents the behavior of light rays passing through a glass? So again, as it goes through, when it goes through here, they're going to spread out. They're going to diverge. Number 55. Which is the correct description of the image produced by a concave lens? So, erect and virtual. The convex spherical mirror found on a passenger side of many cars contains the warning objects are closer than they appear. Which phrase best describes the image of an object viewed? So it's going to be virtual because it looks like it's in it, and then it's going to be smaller, so that would be C. An object is located 0.12 meters, so that's DO, in front of a concave mirror, which is 0.16 radius, so I call that C. What is the distance between the image and the mirror? So I want to find DI. So this is going to be one we're going to have to calculate. So I would just put my piece of paper like this, so I know that DO is equal to 0.12. Now remember that they're telling me C is 0.16. But in my equation, I don't use C, I use F. So F is C over 2, so 0.16 over 2 is 0.8. Now when I use the equation, DI is equal to DOF minus DO minus F. It's going to be 0.12 times 0.08 divided by 0.12 minus 0.08, which is 0.4. Now, so that's answer C. Now with number 58, it says a person, I made the mistake in that I read this whole question and I started doing all the calculations and everything, and the problem was I didn't read it carefully because there's a key word there. And the key word is a plane mirror. So a plane mirror is a flat mirror. When you look in a plane mirror, it says the height of the person's image. It's going to be the same size, remember? It's only if it's concave or convex that the size is changing. So you could say, you could actually, it wasn't until I started writing down the equation and I was like, wait a second. It's the same size because it's a plane. So you don't need to do a calculation there. Here's one of the ones where I'm looking at the picture and it says which diagram best represents a reflection. So if you're looking at something like this, and sometimes some of us, not, we're all different, have a, it's just like doing physics. There's some chapters that you're going to think are easy, some you might find more challenging, and it really varies from person to person. So what I do when I look at this, I would pretend that, it's almost like a vector, like this is the head and this is the tail, or pretend this is a person. So this is their head and this is their feet standing out. So when they look in the mirror, what's going to happen, their head's going to be closer and their feet is going to be further away. What is the approximate speed of light in alcohol? So now we're getting to refraction and we're getting to the indices of refraction. So we want to find the speed of light in alcohol. Well, we're going to use the equation N is equal to C over V. So C is the speed of light in a vacuum, which is 3.0 times 10 to the 8 meters per second. V is the speed in the material, and N is the index of refraction. So what you're going to have to do is, if you looked at that formula sheet I gave you number one, the speed of light in a vacuum. I also gave you the table that has all the indices of refraction. So if we do this, we have V is equal to C over N, so 3.0 times 10 to the 8 meters per second, divided by 1.361. So when you do all that, that comes out to be 2.2 times 10 to the 8, which would be choice B. Which phrase best describes the phenomenon illustrated in the diagram? So we know when one light goes through a prism, what it does is it bends. So the word bending of light is the word refraction, right? Reflect means to bounce off, refract means to, and then because it spreads out, it's going to be dispersion. So refraction and dispersion. As a wave travels into a different medium with a change in direction, there will be a change in the wave's speed. Because remember, as it goes from one medium to another, if the densities are different, it's either going to do what? It's going to speed up or it's going to slow down, right? So again, here we see a picture of light as it goes from one medium to another. Now, if you remember back, we had a couple of tricks to remember these types of situations. I don't remember if we had tricks for the mirrors and the lenses. So anyway, the way that we're going to remember this is our little trick was we're going to remember MLA up. So what does MLA up mean? It means if I go from a more dense to a less dense, I bend away from the normal and I'm going to speed up. So now let's look at this picture. Here I'm going from air to glass. So it's important that I realize what I'm doing. So here I'm going from a less dense to a more dense, which is the opposite of this, right? So I'm going from a less dense to a more dense. So what that means is the speed's going to decrease, and it's going to bend toward the normal, because this is the opposite of what I memorized, my little catchy phrase. So the answer here is D. Which of the diagrams representing light rays reflective circuit diffuse reflection? So diffuse is when the surface is uneven. So even though it shows all the surfaces, really isn't a good picture, because this should be more like wavy. But anyway, when the rays of light bounce off in parallel, that's not what happens. They become scattered. So this is the answer here, is B. Once it hits the surface, they go in different directions. Number 65, a ray is reflected from a surface as shown. Which letter represents the angle of incidence? Well, the angle of incidence means where it's coming from. The reflected ray is where it's going to. So this is the angle here, and that's, when we first looked at the chapter. So remember, we always measure the angles from the normal, and the normal is perpendicular to the surface that is being reflected from. So that's just kind of like the definition. Which is not in the electromagnetic spectrum? So sound waves are not electromagnetic. In the diagram below, so when it goes through, this is a polarizer, because it blocks out one plane of light. Number 68, all frequencies of light have the same speed when traveling through a vacuum. Which phenomena is best explained by wave theory? Interference. Those are pretty much definitions. In a vacuum with light with a frequency of 5.0 times 10 to the 14 hertz have a wavelength of. So this is just like our other equation. Instead of V is equal to F lambda, we have C is equal to F lambda, where C is the speed of light. So now if I want to find the wavelength, lambda is C over F, so it's 3.0 times 10 to the 8 meters per second divided by 5 times 10 to the 14. Now remember, a hertz is 1 over a second. So lambda comes out to be 6 times 10 to the negative 7 meters. But remember, you're going to have time during the exam to go back and check your work. So you don't want to make a silly algebra mistake. This is the type of thing where people make a mistake. So remember, a meter per second divided by 1 over a second is a meter per second times a second over 1. So my seconds cancel, so I end up with meters, which is the correct unit for what we're looking for. So the answer there was B. Number 71, the diagram below shows diffraction. Number 72, the spreading out of the waves is diffraction. Number 73, wave motion in a medium transfers energy only. A lot of these are just definitions and diagrams directly from our notes. Number 74, as two trucks approach each other, the driver of one truck sounds his horn. Compared to the true frequency of the horn when the trucks are stationed, the frequency will be higher. Because remember, because the drivers are moving towards each other, the sound waves are going to get closer together. When the sound waves are closer together, it's going to be a higher frequency. Okay. Number 75, as the driver of a car sounds a horn while traveling toward a stationary person, compared to the sound of the horn heard by the driver, the sound heard by the stationary person. Again, you can visualize it has a higher pitch because they're made closer together and a shorter wavelength. As a wave has a frequency of 200 vibrations per second and a speed of 100 meters per second. What's the wavelength? So this is, again, D is equal to F lambda, so lambda is equal to V over F. So 3.0 times 10 to the 8 meters per second divided by 5 times 10 to the 14. So it comes out to be 0.5. So here's a picture. It says base your answers to questions 77 through 79 on the diagram below, which represents the wave pattern produced by a vibrating source. The pattern is viewed from above. The lines represent the wave crest. The source is moving towards, so it's obviously moving towards point B, because here the source is catching up to the waves that are coming out of it. Number 78, the wave pattern is an illustration of the Doppler effect, which we talked a lot about. And number 79, compared to the frequency of the waves observed at D, the frequency of the waves are obviously higher. Why are they higher? Because they're closer together. So remember, on the test, these 3 questions like this, you could do 3 questions in like 30 seconds. Okay, now we're looking at the physical characteristics of this type of wave. So it says base all your answers 80 through 84 in this diagram. So it says what's the amplitude. So the definition of amplitude is from the rest position here to the top of the wave. So either this is the amplitude, and on the diagram that is from here to here, which is 0.04. So there's no calculation necessary. I just need to look at a picture of a wave and know what the amplitude is. What is the wavelength? So now remember, the wavelength is from where I start to the next successive point of the wave. Okay? So I'm going to start at A. So the next place where A looks is if I go like this. Now I'm back to where A is here. Now, if you look at this whole thing is 2.5. This is not the whole thing, okay? So this, I'm going to look at my choices. So obviously, I'd have to look and say, well, I guess it's going to be 2, just based on the diagram, because it's obviously less than 2.5. Okay, so here I made a mistake. This answer is 0.2 because, again, it's from the rest position to the top, and I didn't look at this closely because I'm half asleep. So from here to here is 0.4, so it's half, which is 0.2, which is from here to here. So don't make that same mistake on the test because you'll probably have a diagram that looks just like this. All right, number 82, if a wave crest passes line XY every 0.4 seconds, the frequency. So frequency is like vibrations per second, waves per second. Remember, hertz is going to be waves per second. So it says if a crest passes line XY every 0.4 seconds, the frequency of the wave, so how many waves per second is going to be 2.5. Which 2 points on the wave are in phase? So the phase just means at the same point. And again, this is just the definition of remembering what that is. So the places that are the same, I have to look at the diagram because every single point there isn't. So C and I are at the same point. Now there might be other points, but they're not maybe here as choices. So I have to look at the choices they give me. What type of wave is this? It's transverse. Number 85, a particle has a frequency of 10 hertz. What would be the period? So remember, period and frequency are the reciprocal of one another. So T is equal to 1 over F. So T is equal to 1/10, which would be 0.1. All right, number 86, in which type of wave is the disturbance parallel to the direction of the wave? So if it's parallel, that means it's going in the same direction. That's the definition of a longitudinal wave. The diagrams below represent undisturbed medium, so we look at these. So this is a typo. This should say compression, not condensation. And that's going to be the correct answer. I think I told you about that typo. What type of wave is produced when particles of a medium are vibrating at right angles? That's the definition of a transverse wave. And then 89, which distance on the right identifies the amplitude? So let's do it correctly. So a amplitude is going to be from here to here. So that's going to be AB. Remember, amplitude is from the rest position to the crest, or from the rest position to the trough, so it could be from here to here, but they don't have that as a choice. And then the last question says, in the diagram below, the distance between points A and B on the wave is 0.1. This wave must have... So remember, a complete wave, the wavelength, is like this. That's the complete wavelength. It would be from here to here. So if this distance here is 0.1, that's a half a wavelength. So they want to know what's the wavelength. So 0.1 times 2 would be 0.2. And that's it. That's the review.